All right, so first let's talk about the risk of an estimator. And more specifically, I want to talk about quadratic risk. So let's say you have any estimator, really, for some population parameter beta. And in our case, this is going to be some estimator for the underlying beta here in the linear regression model. Then this estimator is a random variable in its own right? It will depend on your data. So in this case, beta hat is actually something like beta hat of y. So we'll have an expectation, let's call it mu, and it will have a covariance matrix. Let's call it sigma. And I want to express the quadratic risk in terms of these two quantities. So the quadratic risk was defined as the expectation of beta hat minus beta in Euclidean norm squared. So I just pick an error measure. Let's say I want to know how close is my estimated beta from the ground truth. I estimate it in the Euclidean squared distance, and I want to say how well does it do on average. And then a common decomposition one encounters is the following. Let me subtract off mu and add it back, so I haven't changed anything. And then let's factor out this Euclidean squared distance. So the way this works is you can think about writing this as beta hat minus mu plus mu minus beta transpose beta hat minus mu plus mu minus beta. And then multiplying out, and I want to multiply these two together, then off diagonal terms these two and those two, and then another diagonal term these two, which is going to look like this. Beta hat minus mu norm squared. So I'm immediately pulling them apart using the expectation here, the linearity of the expectation, plus 2 times this term hitting that one and that term hitting that one. So that is beta hat minus mu transpose mu minus beta, plus the expectation of beta minus mu. And I switched the order, but it doesn't matter because it's inside the squared distance. OK, so now look at this. What's actually going on here is that this is the same as the expectation of beta hat minus the expectation of beta hat. And then I can pull this out because this is a deterministic quantity. It's not random at all. And that means that further, I can pull out the expectation. And this is 0. So the cross terms actually vanish. So what remains is this term, which is the squared distance beta of beta hat minus its expectation, and we call this variance. And we call this. So here I can get rid of the expectation because, again, this is not a random variable anymore. And we can call this bias squared. So the thing inside of the norm, we often call the bias, because this tells you how far away the expectation of mu is from beta. So let me actually write the bias so that we agree on a sign. Let me actually write it the other way around as mu minus beta. So this tells you how far away is the expectation of my estimator from beta. Now you could argue that you always want to have something that is unbiased. You always want to say in expectation, I want to get back the original true parameter. But depending on what you're trying to do, that might not be the best choice. For example, if all you care about is having a small quadratic risk, a small mean squared error, then getting a little bit of bias in your variable while simultaneously reducing the variance a lot might be a good idea at the end of the day. OK, so and I want to do one more quick calculation, namely the variance can often be expressed in terms of the covariance matrix of your estimator. And you've seen this in linear regression already. But it's going to be a general fact, namely writing out this inner product, this as an inner product, we obtain this. And now we can write this in terms of the trace. This is a scalar thing, so it doesn't matter whether we apply the trace operator. And now remember your linear algebra. Whenever I have a trace of two matrices, I can cyclically permute them. So in particular, I can swap these two vectors, and it will not change the result. So it's the same as the expectation of the trace of beta hat minus mu, beta hat minus mu transpose. And now I have a matrix here, not a scalar anymore, and I can swap the trace and the expectation because the trace is a linear operator. Which is nothing but the trace of capital sigma. Since the expectation of this outer product is exactly the covariance matrix of your estimator. So that means whenever I know the covariance matrix of my estimator, I also know its variance by just taking the trace over the covariance matrix. Now what we are going to do after we will have determined the distribution of beta hat PCR, is we want to make a little table where we're writing down the bias and the variance of the OLS operator, the OLS estimator, and the PCR estimator. In order to compare them. All right, and for you, how about you think about this in a very specific small example that I'm going to give you later on the page, where you can compute bias and variance and actually see that sometimes introducing a little bit of bias might be a good thing in order to reduce the quadratic risk.